Welcome to 25th session on measure theory. It is the 8th session on Lebesgue integral. Today we are going to prove one of the most basic results. If you notice, we talked about Lebesgue integral, okay, etc., integrability, various things. We rarely computed the Lebesgue integral of any function. But that's the case even with the Riemann integral. You develop a lot of theory, right? And you want to prove monotone functions or Riemann integrable, continuous functions on Riemann integrable, etc. But you very rarely compute using the definition of integral, the integral of the function. Okay. So the best way to compute is due to Newton. If you think of integral a to bf, then if I find a g, so that g dash equal to f, and assume that f is integrable, then a to b, f will be g of b minus g of a. That is the so-called fundamental theorem of calculus. Anyway, so now let's come back. So today what we are planning to do, suppose I have a function f from the closed and bounded interval a, b to r, which is Riemann integrable. Then I want to show it is Lebesgue integrable. And then I want to show the Riemann integral of f over the interval a, b is same as the Lebesgue integral of f over the interval a, b. This is the crux of the matter. Right? Now what are the things we ought to be aware of? I want to talk about Lebesgue integral of a to b. Therefore, the first thing is I have to prove f is measurable. But all I know is f is a Riemann integral function. Therefore, it's a bounded function. So if f is measurable, then it's fine because f is already bounded. Therefore, mod f is less than or equal to m, and m is a constant that is integral over the closed and bounded interval a b, which is a finite measure. Right? Therefore, by the observation we made, f will be Lebesgue integrable. It will be Lebesgue integral. Therefore, Lebesgue integral a to b makes sense. Okay. So one of the important things is to prove f is measurable. Right? Then you have to show both the integrals coincide. Is that clear? Okay. So let us get started. So the major result is the following. Let f from a, b to r be bounded, and that's not necessary be Riemann integrable, because when I talk about Riemann integrable, then f is measurable, f is Lebesgue integrable, and the Riemann integral a to b of x dx equal to, not defined by, equal to integral f dm over ab. Notice that m is the measure, Lebesgue measure, and we usually denote by f d mu. Our mu is m here, and over which is set E, the set E is AB. So to distinguish between Lebesgue and Riemann integrable, this will stand for Riemann integrable. This will stand for Lebesgue integral. Okay, this is the major theorem of today's session. Okay. So what we will do, right. So what we will do will be, we will recall various things. Okay. Let P be a partition, a equal to x naught less than x1, etc. x1 less than b. So this is a partition of the interval AB. Okay, this is standard notation. And our x0, x1, I will call them as nodes. Nodes of the partition. This may not be standard terminology, but I usually use this. Okay. Then what is meant by the measure? See, therefore we have a lot of subintervals. Subintervals are the form xk minus 1 to xk 1 less than or equal to k less than or equal to n. These are the partitioning subintervals. Okay. Then the length of that, namely sk minus 1, this is called the length of the subinterval, and mesh of the partition by definition is maximum of this length. Okay. All right. So we are going to make use of the following result from Riemann integral on Riemann integral. What does it say? F as above is Riemann integrable on AB if and only if there exists a sequence of partitions, if and only if for every sequence Pn of partitions of AB, yeah, before that let me do that. So let us let us look at, once the partition is given, then we define mk of fp, but I will only write a shorthand notation mk. This by definition is the infimum of fx in the interval xk to sk minus 1 to xk, 1 less than or equal to k less than or equal to n. Okay. And capital mk, again the precise notation will be, this will be supremum of fx, okay, over the interval sk minus 1 to xk, right? Then the upper sum of the part, lower sum of the partition of p by definition is little mk into sk minus 1, k equal to 1 to n. Yeah, I hope I'm writing it correctly. And similarly u of p, this is called the lower sum, lower Darboux sum. This is the upper Darboux sum. Right? Now associated with that, there are two step functions. Okay. If you have gone through my first 3 lectures on intuitive geometric ideas of Lebesgue integral, we talked about this. Okay. Let me denote by this S. Okay. Yes, f of p, this step function associated with this. This one of the step function is this one, mk, and the indicator function of sk minus 1 to xk, k equal to 1 to n. And similarly, sigma of p, that is the indicator function, sorry, this is the step function, capital mk, indicator function of the same interval sk minus 1 to xk. Let me make it this open. So the partition I'm thinking of is a equal to x0, x1, and x1 to x2, x2 to x3, and so on, and xn minus 1 to, this is included xn. So this, notice that this function is defined only on the interval a, b, and a and b open, because I have not defined it elsewhere. You understand? So we extend that function S of P at B. By definition, we will let it be this, and sigma of P also. Therefore, these are actually depend on the closed interval now, right? Now notice that S and sigma step functions as in Riemann theory, but they are also simple functions according to us as in Lebesgue theory, right? And they are because they are characteristic function of interval, they are with disjoint, measurable, right, etc. Right? Therefore, the integral, the Lebesgue integral of S over AB, you can see is nothing other than lower sum. And similarly, the Lebesgue integral of this over the interval AB is nothing other than upper sum. Right? This is also equal to the Riemann integral A to B S of x dx. This is also equal to integral of sigma x dx from A to B. Because they have a finite number of discontinuities, therefore we can talk about the integral. Right? All these things are well known. Okay? So just to make sure, okay, I am just essentially reviewing Riemann integral so that the proof will make sense. So this the result we want from Lebesgue integral, sorry, Riemann integral, is the following. F from A, B to R is of course Hessian bounded. Okay, is Riemann integrable if and only if for every sequence Pn of partitions of AB so that the mesh of Pn goes to 0, right? Then what we want to do is we want to say the integral sigma n, a limit of this equal to limit of integral Sn. See, notice that Sn is always less than equal to sigma n. In fact, we have Sn less than equal to, or sorry, what is Sn? I should say what is Sn is S of Pn, Sf of Pn, right? And sigma n is sigma of Fpn, corresponding partition, right? And notice that my Sn is always less than equal to F, less than equal to sigma n for all n. Okay. So these common values will be denoted by integral. This is again A to B sigma nx dx, Sn of x dx, A to B. Since I want it to be Riemann integrable, I am taking these are the Riemann integrable. Okay. Notice that this is nothing other than limit of LF. Sorry, this is upper, right? UF Pn equal to limit of LF Pn, because this is limit of the upper sum, this is the limit of the lower sums corresponding to the partitions. Okay. The crucial thing is this is for any sequence Pn of measurable partitions so that the mesh should go to 0. Okay. So this is essentially the review of Riemann integral. So what we do is we simply fix the notation for the proof. At the same time, we also reviewed basic facts about Riemann integral and the notation. Okay, right. Now, note Sn is less than equal to F, less than equal to sigma n, right? Does it give you how to prove measurability of F? Right? So integral Sn converges to some number, that is the Riemann integral of f. Similarly, integral sigma n converges to the Riemann integral of sigma n converges to the Riemann integral of f. But the Riemann integral of sigma Sn is same as the Lebesgue integral of Sn, the simple function, and the Riemann integral of sigma n, the step function, is same as the Lebesgue integral of sigma n as the Lebesgue in Lebesgue theory. You understand that? Yeah. And Sn is less than or equal to sigma n, right? Therefore, the limit of this is equal to this, right? And there are few things I want to say. Sn converges to some function, sigma n also converges to some function. Okay, I have to make sure they do that. How do I do that? That is why we are going to assume. Okay, in the proof, the Riemann integrability said any sequence Pn of partitions such that mesh Pn is going to 0. But what we are going to assume is that we are choosing Pn in such a way that each Pn plus 1 is a refinement of Pn. Right? So if you remember your Riemann integral theory, then you will know the Sn is increasing. Right? Because, let me recall, that's why I want us to learn thoroughly. It's not just for the theory exam. If you have learned, then you might have forgotten. Okay. So the key idea of the proof is choose Pn so that mesh Pn goes to 0, of course, so that for all n, Pn plus 1 is a refinement. So an easy way would be, suppose my start with P1, P2, P, and suppose Pn is there, right? Then what do I do is I again bisect each of the subintervals now. That I get a Pn plus 1. So obviously Pn plus 1 is a refinement. That will be easier way. So start with P1, bisect AB, and P2, okay, I have A, B, and this is my thing. Then again bisect it. So I get my P2. The nodes are now these. Right? And obviously mesh of Pn is B minus A by 2 to the power n. That goes to 0. Is that clear? And second observation we make is, let us look at my S of Pn of x and S of Pn plus 1 of x, right? Then this is the equal to. Remember, this follows from, whenever Q is a refinement of P, then the upper sum, lower sum f of Q is greater than or equal to lower sum f of P, and the upper sum f of Q will be less than or equal to upper sum of f of P. That is, if you refine better, upper sums keep increasing because we are approximating the area from below, and the lower sums, whereas upper sums you are approximating the area from above. Therefore, when I get a refinement, we get a better and better approximation by reducing. Okay, so if you are not done, please watch my videos on Riemann integral. Okay, so from that it follows. Similarly, T of sigma of Pnx will be greater than or equal to sigma of Pn plus 1x. Right? So now I will write Sn for S of f of Pn and sigma n as a Pn. Therefore, Sn is increasing and sigma n is decreasing sequence. Right? And notice that by assumption, my function f is bounded, say mod f is less than or equal to m. Then my Sn's modulus, they are also less than equal to m, and sigma n are also less than equal to m. In particular, Sn is less, sigma n, Sn is less than equal to m, Sn is less than equal to m, and minus m is less than equal to sigma n. And since Sn increases, the limit, limit Sn has to exist. Call it S of x. It exists because it's bounded, it's increasing sequence, but it's bounded above by m. And similarly, limit n, Tn of sigma n of x, exists. Call it sigma of x. Is that clear? Okay. Notice that each Sn of x is less than equal to fx. Therefore, S of x will be less than equal to fx. Similarly, fx is less than equal to sigma n of x, therefore fx will be less than equal to sigma of x. Because fx is the lower bound for all sigma n, and sigma is the greatest lower bound, therefore fx will be less than equal to this, greater than lower bound. And similarly here. Yeah? The second. Okay. So, we have proved S of x is less than equal to f of x, less than equal to sigma of x. This is for all x in AB. And next thing is, notice that Sn's are measurable, right? And S is the limit of this, therefore S is measurable. And similarly, sigma is measurable. Therefore, my f function is squeezed between two measurable functions. Okay? But that's not enough. So what I would like to say is, this is where the thing comes, right? Okay. The next thing, let us look at now. Sn increases to S, in particular Sn converges to S, and similarly sigma n converges to sigma, right? And all these things are bounded by m. Therefore, by monotone convergence, because m is integrable with respect to the measure, right? Therefore, by dominated convergence theorem or bounded convergence theorem, integral Sn over the interval AB with respect to the measure dm converges to integral of S dm over the interval AB. Do you understand this? And for a similar reason, sigma n dm over the interval AB converges to sigma dm over the interval AB. Okay, pause, review, proceed. Right? But notice that my Sn dm over AB is nothing other than the lower sum of f with respect to Pm. And similarly, sigma n dm over the interval AB is nothing other than the upper sum of f Pm. Since f is Riemann integrable and the measure of Pn goes to 0, then I know L of this should go to integral a to b f of x dx. That's the Riemann integral. Right? Therefore, what we get? Therefore, we get integral a to b Sn dm converges to this number a to b fx dx. This is a Riemann integral. This is a number. Similarly, sigma n integral over the interval ab dm converges to the integral a to b fx dx. Okay, but I know these converge to integral s dm over the interval ab, and this converges to integral sigma dm over the interval ab. Right? Therefore, what is that I have? And also I have s is less than equal to f less than equal to sigma. Okay. Therefore, I know integral of s dm over the interval ab equal to integral of sigma dm over the interval ab. And therefore, this means integral of sigma minus s dm over the interval AB is 0. Notice that sigma minus s is non-negative and measurable, and its integral over the positive measure is 0. This implies sigma minus s is 0 almost everywhere, right? That means sigma equal to s almost everywhere. Therefore, I have my s of x less than equal to fx less than equal to sigma x, right? This is measurable. This is measurable. Therefore, fx, okay, is equal to s of x almost everywhere, or sigma x almost everywhere, right? The sets on which they agree, the exceptional set may be different. Measure of A may be 0 here, where A is a set such that fx is not equal to sx, and B may be the set such that fx equal to not equal to sigma x, that measure is 0. Okay, the sets may be different. Okay, therefore on A union B, the measure is again 0. Therefore, I have fx equal to sx equal to sigma x. I don't need this, but it will be good to know that. Therefore, we conclude f is measurable. Wow. Understand this? And now the thing is clear. S is measurable, F is measurable, and F is sandwiched between S and sigma. Therefore, integral of S must be equal to integral of F. Yeah, but that is equal to integral of sigma also, because these two are almost everywhere equal. Therefore, the integral is the same. Similarly, the integral is the same. But both these integrals are nothing other than integral A to B fx dx. This is the Lebesgue integral dm over the AB. You follow that? Therefore, integral of S over the interval AB dm. But this is nothing other than Riemann integral fx dx. That is equal to integral of f dm over the interval AB. But that is equal to integral sigma over the interval AB. But this is again equal to A to B fx dx. So we have proved, okay, the Lebesgue integral of f dm over AB equal to the Riemann integral A to B fx dx. So pause, review, proceed. So you see that what are the basic ideas? Basic idea is we use the criterion for Riemann integrability in terms, okay, whenever I have a sequence Pn of partitions so that mesh P of Pn goes to 0, then the lower sums of Pn and the upper sum with respect to Pn, they converge to the same number, and it, okay, then that number is called the integral of f. Alright, integral of Riemann integral of f. Okay, that we got to use. So what are the tricks we did? We did not take any Pn. What we took was Pn is a sequence of refinements, right? Pn plus 1 is a refinement of Fn. Okay, and in fact we got Pn plus 1 by bisecting the partitions of Pn. Okay, therefore the mesh automatically goes to 0. Then the next thing we observed was I looked at the corresponding step functions or simple functions Sn and sigma n. Now because of this refinement, I know that Sn is increasing sequence and sigma n is a decreasing sequence. Therefore, the limit of Sn exists and limit of sigma n exists, and they are measurable. My f is sandwiched between these two limits, right? Therefore, I conclude f is measurable. That is the basic idea. Yeah. But then to prove that, what did I need? I have to make sure S equal to sigma almost everywhere. How did I do that? Go through the proof. This way of reviewing makes you understand the proof, not by line. That is good to write in an exam. Okay, write on a blackboard so that line by line we can check logic is correct. But how do I get the mastery over the proof? This is how we have to review. Yeah, please go through it. Now we will continue with the next one. So the next result we want to prove is the proof shows something more. It just shows if f is Riemann integrable, then it is continuous almost everywhere. For most often, if your analysis course has been good, you might have proved in real analysis itself. You would have defined a set of measure 0 there and proved that the set of points of discontinuity of measure 0 of a Riemann integrable function is 0. Okay. The measure of the set of discontinuities of a Riemann integrable function is 0. You would already proved it. Okay. But our proof actually gives another way of looking at it. Okay. And to be very honest, it may not be in a textbook, it may not be taught in a course, so naturally it will not appear for exam. But don't worry, by going through the proof you will understand how to deal with measure theory, integral, etc. Okay, as I said, think of this as a training ground. Okay, after that you can read your class notes or a good textbook and learn the proof as your teacher or examiner wants you to write. Okay, let us go to the step. Now what I want to prove, suppose f is Riemann integrable. So we want to prove the following thing. Suppose f from A B to R is a Riemann integrable. Then f is continuous almost everywhere with respect to the measure f, Lebesgue measure. Okay, let us just try to see what should be the idea of the proof. Notice that how did I get f? How did I prove f is measurable? By saying that S is sandwiched between f and sigma, and because integral s equal to integral sigma equal to the Riemann integral f of x dx, okay, this is the Lebesgue integral. Therefore, integral of sigma minus s is 0. Therefore, sigma equal to s almost everywhere, etc. Alright. So, my f is going to, in some sense, going to coincide with s and sigma almost everywhere. Right? That we had already claimed. Therefore, now look at any s is the limit of Sn and sigma is limit of sigma n. Now let's look at Sn. For example, they all involve only characteristic functions of intervals of the point sk minus 1 to xk open. Right? Now, therefore, this is a kind of thing. Therefore, the only points of discontinuity are here. You understand that? And for each, okay, for each Sn and Tn, okay, yeah, and there is also a set f where the set x so that either fx is not equal to sx or union of fx is not equal to sigma x. That's what we call a and b, if I remember right, and a union b is a measure 0. Right? My f coincide only ss and sigma x. Right? Therefore, my guess is if we call this as C to be the set of nodes of all pns. Pns are as earlier. That is, pns are refinements of the previous ones as we did by bisection method or by any method, doesn't matter. Okay. So notice that this is a countable set. Because for each pn I have only finitely many points and there are countably many pn. Therefore, this is a countable set. Right? Therefore, the A union B union C, call it E, or if you want to call it D, this measure of D is 0. Okay, pause. So these are the likely points where my f may not be continuous. Okay, this is intuition. I am not claiming. I have to prove that. Okay, so we claim that. So we wish to claim if x is in AB but not in D, then f is continuous at x. right? Do you understand? Therefore, the first thing is whenever x is here, call this at E. Whenever x is in E, notice that fx equal to Sx equal to sigma x. Right? Okay. And the next thing is x is not in any of the nodes. It's not a node of any partition. These are the obvious things you should keep in mind. Okay. So we shall prove this by contradiction. Then we will arrive at a contradiction. Okay. So how do I plan to do that? The first thing is f is not continuous at x. That doesn't mean what? There is an epsilon positive. For every delta positive, there exists a y in x minus delta to x plus delta, so that modulus of fy minus fx is greater than or equal to epsilon. Notice that since x so is not in any other partition, I can assume there is a delta. This x minus delta to x plus delta, that will be contained in that. I can always find one such y. This is the definition of discontinuity at x. Is that clear? This is a logical thing. That is one of the reasons one should watch my videos on foundations. Your logic should be correct. Okay. Now let's come back. Right? So what do I want to do? Yes. Right. Yeah. From this I want to conclude. Okay. I want to conclude for each n, then sigma n of x minus Sn of x, okay, is greater than or equal to epsilon. We want to claim. Okay. Once you understood the rest of the proof, assume this for the minute. For a moment, let us complete the proof. Okay. That means by passing to the limit, this will be greater than or equal to epsilon, but that's a contradiction. Because x belongs to E, that means yes, sigma x must be equal to S of x. Is that clear? So this all I have to prove. So we have to prove for each n modulus of, not modulus, sigma n of x minus Sn of x is greater than or equal to epsilon. Okay, that is the, then in the limit sigma x minus x is 6 greater than or equal to epsilon, but x belongs to E, therefore sigma x equal to S6. That's a contradiction, right? So how do I prove that? Okay, let us prove it, then the result will be complete. So sigma nx minus Snx is greater than or equal to epsilon. Since f is not continuous, then okay, we know that for every epsilon positive, there exists epsilon positive, so that for every delta positive, I can always find a y in x minus delta to x plus delta, so that modulus fy minus fx is greater than or equal to epsilon, right? Now look. Suppose now my x at the nth stage, it belongs to one of the partitioning interval. Remember, x cannot be the boundary points because the nodes are excluded. Therefore, it has to be interior point. And suppose y is also here, then what are the possibilities? Let us look at fy minus fx. Okay, here on this partition subinterval, my mn is the supremum of ft, and small mm is the infimum of ft, not modulus, just ft, as t varies with the xk to xk plus 1 or xk minus 1 to xk, etc. Whatever the partition subinterval at the end stage, right? Therefore, what I know is this is less than or equal to mn, because fy has to be less than or equal to this, and fx is greater than or equal to mn, therefore minus fx will be less than or equal to minus mn. And interchange x and y, I get the same thing. Fx minus fy will also less than or equal to mn minus mn, right? But notice that this is nothing other than sigma n of x minus Sn of x, because x lies here, right? Therefore, these are negative. Therefore, that means mod fy minus fx. Okay, this I know is greater than or equal to epsilon, but that's less than or equal to m1 minus mn. But that is sigma n of x minus s of x. Therefore, what I have shown is for each n, sigma n of x minus Sn of x is greater than or equal to epsilon. Therefore, then the limit sigma x minus xx is greater than or equal to Sn, but x belongs to E, that means sigma x equal to Sx. Right? Therefore, what I have proved is if x is in E, implies f is continuous at E. Right? And we all saw that the interval AB minus E, these are measures 0. Therefore, f is continuous almost everywhere. Okay, that proves it. We can also go ahead and prove f is continuous almost everywhere. F has to be f has to be Riemann integrable. Okay, but I don't want to do that. My only point is to prove this. Okay, how the Lebesgue integral, Riemann integral of a bounded function relates to the Lebesgue integral. Okay, we have proved it. That is what is needed. And the importance of this is, as I said earlier in the beginning, we talked about integrability, various other things, various properties, but we never knew how to compute. Now, if I have a function f, okay, which is Riemann integrable, therefore to compute the Riemann integral, I can use fundamental theorem of calculus, assuming there exists a primitive, integral a to b, integral of f over the integral ab equal to integral of f a to b with the Riemann integral, but that is equal to g of b minus g of a if g dash equal to f, etc., etc. Okay, therefore whatever you learn about in Riemann integral after fundamental theorem of calculus can be used here freely. Okay, and in fact I can also directly prove fundamental theorem of calculus for using Lebesgue measure, but I do not spend such time. That is not needed. Okay, so we will make use of it. Okay, I hope you understood what I am trying to say. Yeah, for example, if I want to say integral of x squared from 0 to 1, okay, now x squared is Riemann integral, therefore the Lebesgue integral is the same, therefore I can using the fundamental theorem of calculus, it is x cubed by 3 between 0 and 1, therefore it is 1 by 3, etc. Right, we can do that. Okay, yeah, but then what is the purpose of Lebesgue integral? We will see that in action later. Okay, I just hope all of you liked it. First, go through the first part, understand it very well. Okay, the second part is, as I said, it's very easy. Okay, and it told you if f is Riemann integral, it's almost continuous. Whereas we have seen there exist functions which are nowhere continuous, like the Dirichlet function, but it is a Lebesgue integral. So you can see the contrast. That is the reason why I wanted to do that. Okay, because Riemann integrability enforces a very stringent condition. The function has to be continuous almost everywhere. Whereas we have seen functions which are nowhere continuous but Lebesgue integrable, namely Dirichley's function. Okay, keep that in mind. Okay, I hope we will meet again. Take care, stay safe.